Mm. Greetings to everyone watching this project presentation of Fragment 3D presented by group number 706. This is KJ and Karthikeya under the mentorship of Dr. Shilpa Chaudhary here to present and give an overview of the project in the final Milestone 2 video. Let us get an overview of the project once again. Our project is to create an end-to-end 3D object generation framework that allows generation of 3D objects as separate editable parts from a single image. Though there are many other platforms or websites that look like offering the similar facility, the key difference between this project and the websites are they develop a single mesh of 3D model that is non-editable, so it's just merely a showpiece and of no use, whereas this project mainly caters that need and focuses on developing separate fragments of the 3D model so that it is used by professionals like animators or 3D model artists. Let us get an architectural diagram overview of the project. We have a React-based website that is used by the user to upload image, login, register, or sign up onto the platform. Whereas after logging or signing up, the middleware of Node.js and Express.js through API calls of Gradio API and the database handles the workflow. We can see that the uploading of image is done between Express.js and the database, and after, if the image is already available in the database, it is being called through the asset ID. If not, a separate asset ID is being created, after which the generate command is given to through the Gradio API. We can also delete the existing assets from our own logged in ID if we want to. If we focus on Gradio API, we have used Gradio API since the project uses high GPU computational power. It would be easier through Gradio API to interact between the user and the platform. If not, it would be a hectic and complex work. If we go into the flow of data inside the project, first we have the encoder to extract the key features from the input image, and after that random noise is added to the picture in order to start the denoising process, after which the decoder extracts the latent vectors of information that is uh, encoded by the encoder, after which we use the dual volume packing to pack the different volumes generated through this into a single volume. And finally, we have the triplanar extraction, which is the key part of this project and which is responsible for decreasing the computational power over the regular models. This part mainly focuses on decreasing the computational power instead of by generating the whole image into 3D voxels. We focus on the key features and key points in the 3D grid, and then we convert them into voxels, which in turn doesn't affect the clarity of the image and also decreases the computational power. If we move on to the tech stack of the project, the core development is done through Python and the framework is PyTorch. The generative model, which is of dual volume packing, has used libraries of PyTorch. The 3D representation is done through fast hash grid 3D representation, which is backed by NVIDIA Tiny CUDA neural network. The development tools in the front end and model are VS Code, Anti-Gravity, Colab, Jupyter, as mentioned, and the database we are using is non-SQL database, which is MongoDB. And since we are using images, it is recommended for us to use MongoDB instead of SQL or other NoSQL based databases. If we move on to the mathematical foundation of this project, first is the latent decoding and global context. The latent representation, if done by the encoder, can be thought as Z, and the Z is passed on to the decoder, which maps the Z to a sequence of global hidden states. Let us name it H, and this is done through a hidden state of global states. And later we move on to the global feature projection. First, we compute a pooled global description from the transformer outputs. This is done in order to decrease the computational power. Instead of directly taking the whole data, we do global pooling. The vector is linearly projected into the three orthogonal feature planes, which is xy, zx, and yz planes. And after, from each plane, we extract those points and align them into a vector. And later, the bilinear sampling from the triplanar feature happens, where the random point from the 3D grid is extracted and is uh, placed or positioned over the three planes, which gives us an average value for each plane. The average is then taken through the triplanar feature aggregation. The average of the three planes gives us the data of the 3D point in the 3D grid. This step is a key step because this maintains the clarity of the model being generated. It also decreases the high density of points that is possible in such complex models, and also decreases the computational power through a large margin, to be precise, or approximately over 60%. We move on to the live implementation of the project now. Let us start the implementation of our project. This is the login or sign up page of the project Fragment 3D. We can log in through already a signed up ID. Let us log in through the already created ID. As we can see, this is the history of the previously created objects, a rabbit, a car, etc., etc. We can also proceed to delete existing models. And if we move further, we land up on the home page once again, but we do not get logged out of it as we have already logged in. And now moving on to generating a new 3D model of a random image. Let us upload the image of a chair. The segmentation of the image is done by the model, and now the 3D model is being generated. Yeah, the model is finally ready. We have got two different fragments. As we can see, if we explode the image, we have got two separated volumes. This will also be recorded in the history of this account. Let us upload another image. The segmentation of the image from the background is done. Since the 3D model of this image can be complex, it may take some time. Till then, as we can see, the history reflects the recently developed 3D model and also the generating 3D model. The 3D model has been generated, and if we explode the image, we have got the separated volumes, though there is a bit error due to the background issue, but the model is successfully created. Our implementation architecture alignment, we have injected our custom triplanar layers and validated that they could process the pre-trained features without causing catastrophic forgetting or structural collapse. controlled integration, we injected new code logic into the pre-trained model structure while maintaining the original high-quality performance. End-to-end pipeline. Fragment 3D achieves end-to-end generation of part-level 3D objects from a single image without relying on external 2D segmentation priors. This simplifies the pipeline and mitigates the risk of error propagation from inaccurate segmentation. The potential improvements of this project include fine-tuning and training. The logical next step is to fine-tune the new triple head weights while keeping the original attention weights frozen or lightly fine-tuned to see if the triplanar representation can learn to encode the part level information without relying on original attention output. And we can also improve on developing more reliable and consistent part annotation and extraction processes to address the issues of noisy or inconsistent graph information. Real world applications of this project are, as discussed before, architectural and industrial design prototyping, rapidly generating editable models for furniture, machinery, or complex products from an initial image concept, game development, generating 3D assets that are already decomposed into semantic parts, structured 3D content creation. End-to-end efficiency makes it a powerful tool for rapidly creating a large volume of editable and structured 3D content. Major challenges during this project implementation were: this is a computationally expensive model. We overcame this by implementing a triplanar feature projection that compresses 3D space into efficient 2D orthogonal planes, reducing memory overhead by approximately 60% as mentioned before, while maintaining distinct part separability, maintaining pre-trained quality. Hybrid strategy by creating a parallel triplanar to fulfill the implementation of new logic. In conclusion, this project contributes to the broader vision of human-centered 3D creativity, where neural networks not only replicate visual forms but also understand and generate the structural logic behind them. We intend that this project can even be much more further developed and can be used in various fields and be much more accessible to people than it is now. Thank you.